Hello, this is now a discussion on the simulation of network epidemics while using the R package iGraph. In a previous discussion, we used a simulator for network epidemics that is called NetLogo, and we could see on real time how each vertex in the network was switching between states, and there were three possible states denoted with the letters S, I, and R for susceptible, infected, and recovered. So here, an important thing is while before you do anything with this R package, you have to invoke the library, right? So you have to make sure you have library iGraph. That should be the first command. And one thing to contrast between this type of simulation versus the previous simulator, in the previous simulator, we were able to see the simulation on real time, but we were only seeing one of those over the course of the epidemic. With iGraph, we can simulate simultaneously a number of repetitions, and these repetitions in the context of stochastic processes are called stochastic realizations. So we're going to see here some of the basic, very basic commands for simulating an SIR model. So the first thing is to define an object, graph object under the library iGraph. And this could be by using a data set, or it could be by using some of the built-in functions for constructing or generating networks or graphs in iGraph. So here, as an example, I'm using a graph that is generated with the algorithm based on Barabasi and Albert. So here, this is referred with this command, and these are parameters of parameters for the network model Barabasi. So this is specifying that we want a network with 300 vertices, and this is an additional parameter of how that network is built by adding m edges at the time. So I can surely refer you to the documentation of iGraph, but with these two simple parameters, we'll be building a graph with 300 vertices with specific scale-free properties based on as an implication of this type of built-in graph. And the next thing we specify are the epidemic parameter values, which in this case are set to these values, and then the number of repetitions is set to be equal to 10. So with iGraph, the command SIR will simulate the SIR epidemic model given a specific network. So this is a simulation of the network epidemic known as SIR. Then we pass the epidemic parameter values, and then we also pass the last argument here specifying how many repetitions. By doing so, the program executes, and then I'm calling the variable, which is the output of this call to the function SIR. I'm calling that variable X, so you can plot that variable, and you would obtain this type of display. So this here is automatically displaying the number of infected individuals versus time. So the horizontal axis is time, and is light blue. Each curve in light blue is a run of the simulation, and there are 10 of those curves. And then there is a representation here with a dash curve and the solid blue. So I'm going to let you explore and determine what is the meaning of the solid and what is the meaning of the dash. You may want to think of this as some type of interquartile range at each time step, okay? But I will let you confirm exactly what is the meaning. I do want to comment on the following, and is that this function SIR is going to output an object. In fact, it's going to output a list, okay, with one element for each simulation. So one element on this list for each simulation. In this case, we had a run with 10 simulations. So let me demonstrate for you using the R console. So here we have exactly those lines of R code. So I'm going to highlight this. I'm going to run those lines of code first. Then I'm going to highlight this line 7. I'm going to execute that line. So I highlight all these portions of code. I hit run. Please ignore this warning message. This is not necessarily an error, but rather a warning. And I'm calling the output of SIR X. If I type X here, we're going to get large number of things there. So let me now point to this section here of the environment. We take a look at the environment. In the global environment, there's a list of X, and this says that X is a list of 4, and each of those 4 contains an attribute called times, another attribute called ns, ni, and nr. So there are 10 repetitions. Excuse me, here maybe I'll run this. Let me run this with 5 repetitions, so I won't re-execute this for purposes of demonstration. Okay, so now we have a list of 5 here for X, and each of those 5 contains those arguments. So if I go to the prompt, the console, and type X, I get a bunch of numbers, but now I'm going to type X, and I'm going to use this double square bracket. This is syntax for accessing terms, accessing the lists, each list on that object. And now I'm going to access the first of this. And so what we see is that that first term contains times, ns, ni, and nr, right? So if I wanted to look at the first attribute there, I do this. If I want to look at the ns attribute, that displays the number of susceptibles, the number of infected, and the number of recovered. Okay, so these are stochastic simulations. Some of these simulations of network epidemics will die. Eventually they die off, right? But some of them will die sooner rather than later. Let's look at now the second list. And we can see in the second list there is a lot of entries. So let's look at, for example, the number of infected. There are, after 591 steps, those number of infected die off to 0. The number of susceptible, eventually it starts with 299 susceptible, and eventually this ends up in 1, and then there are all these numbers for the number of recovered. So what we see if we plot here, if we plot X, what we see if we plot X is a display of the so-called realizations of this simulation, right? Each of them here in light blue. But it's a display only of the number of infected individuals in the simulations. So you would have to do a little bit of thinking if you'd like to display the other numbers in these simulations, which are the number of susceptibles and number of recovered, right? So automatically, by using the command plot, there is a display of the number of infected in the simulation, but it is also possible to access the number of susceptibles precisely by doing this, right? So using the double square brackets would allow one to access different realizations on a given run. So using the same parameter values for the network model and the same values for the epidemic model, we can do now a simulation with 50 repetitions, 50 realizations, and this is a display on these realizations and the number of infected individuals. This is another run for 100 repetitions. And so for 100 repetitions, then this would be the outcome. Notice that all we're changing in these lines of code is the value of this variable, which is going to be the number of repetitions, number of simulations. And as a last illustration, if we repeat this 5,000 times, if we repeat the simulation 5,000 times, I had to change the value of this simulation parameter, and I had to enter there 5,000, run the simulation, and that would output this type of plot. Each of these light blue curves is a realization of this network epidemic of the type SIR. Right, so you can see that at each time point, there certainly is a level of variability on the potential for the random number of infected individuals on this type of network obtained using the Varabasi-Albert network growth model.